to lectures 23, 24 on the course Thermodynamics of Materials. So we are discussing thermochemistry and effect of temperature pressure on enthalpy change. We started studying effect of temperature, effect of pressure on enthalpy change last day. So refer to the last day. Last day's class. So you can refer to the last day's class. What we found? We actually consider two types of system. Remember? Okay. Two types of system. We will consider. What is this? Fixed mass 1, fixed mass and fixed composition system. And second is variable mass with or without variable composition. Okay. In the last class, we discussed fixed mass and fixed composition system, variable mass. Now, okay, example is, okay, what is the example is? Example, I discussed this, is fixed mass and fixed composition means, example is pure substance. Pure substance with a given size. With a given size means fixed mass. Size means mass, volume. And pure means composition is fixed, pure substance. Mole fraction, we say composition given by mole fraction. So pure means 1. So pure, this is the example. What is the example for this? Example for this, this is the example for this. And example for this, example 1 is chemical reaction systems. Chemical reaction systems. Achha, let me write here. Example is what? E.g. 3 moles argon. Okay, or okay, 3 moles argon, or say B 4 moles iron, pure iron. C 5 moles or 1 mole water. So on. Okay, iron solid, liquid, gas. What is this chemical reaction system is what? Yeah, it's like say M plus O2, M solid. Just right now. M plus O2 goes to MO2. This simple reaction. Or say another one, CO plus half O2 is CO2. Chemical reaction system. Another is this solution system. Solution systems like say iron, manganese, silicon solution. This type of systems we will consider, okay, in solution thermodynamics, and chemical reaction system we will now consider. Now we are discussing this. Here I tell you another thing, or it can be these are variable mass and variable composition. Okay. So let's start now. So we are discussing fixed mass and fixed composition system last day. Remember, effect of study last class. Effect of pressure on enthalpy of this enthalpy. Enthalpy of a fixed mass fixed composition system, like say of a pure on enthalpy of a pure substance. Last class, what we got? What is got? N moles of A, temperature T, effect of pressure means temperature constant. This we found. Just I missed. I want to add something here. What is the constant temperature? What is the delta H? Your question is delta H. So how do you find dH first? dH is, as I told you, Ncp A dt. This is effect of pressure. This is different. V into 1 minus alpha T dP. This I said. And if it is n moles, it is molar, then for n moles it will be n moles. Or delta H will be integration. N may be outside, V into 1 minus alpha T dP from P1 to P2. This was the answer. Effect of pressure, how if pressure changes on a pure substance, like this is the pure substance, it changes the pressure. 1 atmosphere to 5 atmosphere on this. Then its enthalpy will change. Temperature remaining unchanged. And first one is, we have already discussed effect of temperature on enthalpy. When pressure is constant, that means constant pressure with increasing the temperature. From T1, say 300 Kelvin to 500 Kelvin, subjected to same pressure of 1 atmosphere. Now what is the enthalpy change? We found yesterday, Ncp dt. Ncp dt integration between the T1 means 300 Kelvin to T2 500. This was discussed. This was also discussed. But why have I taken up this? You said that it is 0, sir. Remember, you said, but it is true, but true for only a special type of system. What is that? Ideal gas. Say 3 moles of ideal gas, 1 mole of ideal gas. It is correct answer. But if it is for generally speaking, it is not. Okay, we have to consider all kinds of system. Fixed mass, fixed composition means you have seen already, solid, liquid, gas, all possible. So, but I will show you that this is satisfying. That this also reconciles with the relation that delta H for ideal gas. When pressure changes, keeping the temperature constant is what? 0. This we know. I mean delta H, this would be 0 for an ideal gas. So why this will be what? Is for ideal gas special case. Check. You know for ideal gas you know 0. Special case, ideal gas. For ideal, what is alpha? Quickly find 1 by V del T at constant pressure. So when I put N means it is moles and molar volume. So it is. So what is this value for ideal gas? P is RT by P for 1 moles molar. So what is del V del T at constant pressure? R by P. Substitute this here. R by P is R by PV. R by PV is R by PV is for 1 mole. R by RT. You know this value for this is known as isobaric expansivity. Name is last day I told you isobaric because constant pressure. Isobaric expansivity means coefficient of expansion, volume expansion. This is your high school information. So, but what value this is? This value, this coefficient of volume expansion for ideal gas, you know what is the value? Alpha. Alpha is 1 by T. As you see here, is uh, this R by RT is what? So this is the answer. Alpha is, remember, alpha for ideal gas. Isobaric expansivity for ideal gas is 1 by T only. Substituting here, if you substitute this, what we will get here? So this leads to what? Delta H is what? Is what? 0. Why 0? Alpha is 1 by T. So alpha T is 1, 1 minus 1 is 0, whole thing is 0. So, okay, agreed, okay? So reconciled, maybe, right? Reconciled. Or say same result. So this is the general expression for any system. Very good. Effect of pressure. Huh? Next is today. So this is about fixed mass and fixed composition. Now we consider very chemical reaction system. Okay, that is chemical reaction system. Follow this. What is this? I am writing. So I take for example M solid plus O2 gas is MO2 solid. This is the reaction. This is occurring at constant temperature and constant pressure. This is the study. E.g. this will study. Now it's interesting. Constant temperature, constant pressure. Is there any possibility of getting delta H in case of fixed mass, fixed composition system? Two things are constant, temperature and pressure. Fixed mass and fixed composition system, say example, say 1 mole ideal gas. For you, easy. Any since check with the simplest one, ideal gas. 1 mole ideal gas, if two things are constant temperature, constant pressure, any process can occur. Can any process with ideal gas? Two things constant. We have read this isothermal means one thing constant, temperature constant. Constant pressure means pressure constant. Constant volume means volume constant. And adiabatic means non-constant. But two constant means everything constant. Because given size, 1 mole means given size. N is not a variable. Number of moles is not a variable. If it is variable, then there is change, because if you add change the number of moles. But 1 moles ideal gas, so two things constant, no process can occur because everything is fixed. Initial state and final states are same, so no process. But if it is a chemical reaction system which is a variable mass with or without variable composition, this I will explain. With or without variable composition is what. So this is here enthalpy change will occur. So enthalpy change you have found, expression you have found here, expression you have found. Okay, and okay, this you have seen. Okay, so let us see what is the expression. Similarly, another expression is effect of temperature for fixed mass, fixed composition. Delta H is what? N. Delta H, recall delta H is N. Tell me right. Delta H. Tell me last year. Effect of temperature. Effect of temperature. Here, effect of temperature is what? Delta H is. Is what? Effect of temperature. We got delta H is, tell me, N Cp A dt T1 to T2. That is effect of temperature for temperature. Okay, for the process N moles of A at what temperature? Temperature changing effect for the process. This is T1. For the process what? Pressure fixed, temperature changing. Goes to N moles of A, pressure fixed, temperature changing. What is the delta H? Delta H is this. This is one. This is the second you started already. Today, yes sir, both are constant. Means no change. Then what is this? Let's start with this. I will show you something. Let's start systematically. H prime for extensive property I am writing is function of pressure, temperature, independent variables I am writing. Nm, NO2, NMO2. Right, these are already discussed, right? These are right. These are already discussed. Okay, already discussed. Right somewhere, huh? Already discussed last class. Last class. Today, huh? Today, we just give it today so you understand. Today, we consider chemical reaction system. This is the reaction. How we write this? Enthalpy is a function of, it's okay. Enthalpy is a function of, is what? Is independent variables. This is the independent, this is the dependent. In the pressure temperature, I can independently take, and this is what I tell you. Just see how you write. I told you this when I discussed independent variable and dependent state function. Okay, dependent variable. So what is this? You follow this. This is your system. See what is the meaning of this. This first line is most important. If you follow the first line, it is much. Year to year. If you follow, everything will follow. Rest is mathematical exercise, calculus only. I will differentiate soon. That's not big deal. Big deal is what? Why you wrote this, sir? What else you could write? The reaction is n plus O2 I will carry out. For this mathematical representation of is this, okay? So what I am taking, see follow. I am taking arbitrary. This is independent variables means arbitrarily, independently. So I take independently 10 moles of N. I took means it is the moment I take 10 means it could be 11, it can be 1, so it goes there, so independent as an independent variable Nm. Then I take 5 moles of O2 gas. Again see it could be 6, so again independent. I can see, you might say if it is clashing anywhere, then I cannot write, but there is no class, you check this. And 7 moles of MO2, also maybe 3 moles of MO2, maybe. Product I also take, product I can take, it can be 0 when you don't take. The only reactants, typically we take only reactants, but you can take products also, big generalized things, okay? Try to generalize, you can make any values, okay? Again see, I can write, I can take. And what else I have done that I should have mentioned, I am now mentioning, I have thermostated it with temperature. T is perhaps any temperature I am interested, say sir 1000 Kelvin. I can thermostat this. Any temperature I can do. It can be 1100 degree. It can be 500 Kelvin. That means again temperature goes there as an independent variable. What pressure here is any pressure I can do, sir. I can 1, 2, 3. I'm not using 1 in case you consider that it is always 1. No, anything. 2 atmospheres. Sir. So see, independent. 2 means it could be 1. It could be 3. So I can maintain this. I can take. I'm the experiment. I'm taking in a reservoir, in a container with this temperature pressure facilities. Temperature. Yeah, these certain number of moles of MO2 and MO2. And which is thermostated at a given temperature, and which is actually under a pressure, certain pressure to atmosphere. Then, if I can do this, I'm entitled to write this. You cannot see, for example, contrast. This is chemical reaction system. Chemical, for reaction will occur, you understand. At this, now reaction, this is initial state. Then reaction will take place, and metal will be consumed, oxygen will be consumed, metal oxide will be produced and will be added to whatever already present. This is the status, chemical reaction system. The reaction, obviously reaction must be known, otherwise chemical reaction means, what is the reaction under study? Reaction under study is M plus M solid plus O2 gas goes to MO2 solid. This is our discussion. First line, okay. Now you see, you may say, sir, every time I can do this. Let us try. With fixed mass, fixed composition, can you do this? This will be very interesting. Can I do this? Let us try. I'm trying. In contrast, can we fix T TP for fixed mass fixed composition system. Fixed mass fixed composition. I'm writing actually. I have to write. Otherwise, no way to explain this. Fixed composition system. In contrast, can we fix temperature pressure for a fixed mass system? Question mark. In contrast, can we? Answer is C. You understand? Try to do this, sir. I am taking fixed mass example e.g. Fixed mass means a given size of ideal gas. Say 3 moles of ideal gas. 3 moles. 3 moles of e.g. of ideal gas. Argon maybe. I take. So sir, very good sir. Start. 3 moles means given size. Given size. It is not my choice. So if I write here H prime is a function of. Similarly, I am writing in this case 3 moles means given size means it is 3 moles given. You cannot make it 4 moles anymore. Anyhow. Okay, 3 moles means 3 moles function. So I cannot start here. What is the temperature, sir? 3 moles ideal gas, right? Ideal gas. What is this? Okay, 3 moles ideal gas. Very good. What is the pressure? Temperature is 1000 Kelvin. Pressure is 2 atmosphere. Okay. So freely, actually, this is actually, I tell you what. So what is this? Then what is happening here? H prime is a function of temperature 1000 Kelvin. Okay, you can take 3 moles. Then what is happening? If you given size, then volume is fixed. Okay, so what happens? Okay, so 2 atmosphere function of you can write 2 okay, pressure, temperature. Right, let me write. 3 moles. 3 moles I am not writing because that is not variable. That's given, fixed. You understand? This is not a variable anymore. H prime is a function of pressure, temperature. This I have written. H prime is a function of pressure. That means, now follow. So one thing, N is excluded. Let's try. Similarly try. So pressure, temperature, 3 moles. Pressure, temperature in this system, what will happen? Can you change the pressure? Can you change the temperature? Okay, with this system, okay. Can you change the pressure? Can you change the temperature here freely? 1000 Kelvin. The given size, pressure, temperature. No. What I said actually, 2 you can fix always. 2 you can for a given size. Oh, that's right. The system is actually you have see pressure, temperature. Moles you cannot write. So this is okay. This is possible. Pressure, temperature you can change actually 1000 Kelvin any. So volume is actually, I tell you what, fixed. Volume is nRT by P. Write this. So you see this is fixed. So you will actually what I tell you what 3 moles. The volume will P is nRT by P. So if you change this pressure, temperature, what will happen? 3 moles. That's right. It's okay. So this, I tell you what, this system is actually, volume is what? nRT. Let me write 3 R, temperature is what? 1000 for example, 1000 Kelvin. Pressure is what? 2 atmosphere. That means it's a fixed atmosphere. No, I'm sorry. Okay. Yes. Actually, we can write this. This is okay. This is okay. What is not okay? Same way is function of pressure, temperature in gas. This can we write in this case? We cannot write. We cannot write. What happens actually, I tell you what, this also we can write. This also you can write, but remember this. This is actually very good, very good. When I write this is example of, this is an example of, acha, right, since I've already started, very good. This is an example of, right, what is this? Fixed, okay, fixed mass fixed composition with fixed mass fixed composition system. Fixed mass, once I'm writing repeatedly, fixed composition system. Try to follow this, follow this. Actually, I have noted this. See, if you volume will change. Anytime you have 3 moles ideal gas fixed, then temperature, pressure are the two things that you actually have. Okay, two variables. I told you two actually independent variables. So if you have fixed this, then volume is determined. Value is fixed. What is called dependently. Fixed dependently. Fixed dependently means I can independently fix this volume. This is the meaning of this. I cannot take. Okay, but I can make volume also independent. How follow this? I can write this also. This I am writing when fixed mass fixed composition. When I can write this? Tell me. N gas means N ideal gas. I can write variable mass. Yes, I can write. This is true. Mass is variable. I can take 4 moles. Follow the difference. Follow. This is I have taken since 3 moles. Then I have fixed these 2 and fixed 3 moles. Okay. This is fixed mass fixed composition system. Fixed mass fixed composition system. And this is the mass is variable. I will take this temperature pressure fixed arbitrarily. Then I take 4 moles. That I can take. Then what will happen? Difference will be what? Volume will be changing. Other things same. 4 moles volume will increase. Okay. Let it be. But I can take. So 3 moles. What does it mean? When you have fixed 3 moles, you don't have any choice about the volume. You have no volume cannot be an independent variable anymore. Volume is fixed. But when you have taken N gas, that means I can take, I'm telling, arbitrarily. So what I write arbitrarily. Say what is the pressure? 2 atmosphere. What is the temperature? 1000 Kelvin. These are all arbitrary values because it could be changed. N gas, yes sir, it can be 3 moles, 3 or 4 or 5. Then what is the difference? Yes, you can write this. Then what is the name of this? Tell me now. It is a variable mass. Effect is what? What is the manifestation? The moment I vary the number of moles, the volume will be greater. But all the same, these are independent. Volume will be dependent. So I told you once that PTV you cannot write, na? PTV you cannot write. So forget about volume. What I am telling, can I take with a given mass, I have pressure temperature. What is this? You cannot write volume here. If you want to get back to the previous knowledge, you cannot write volume here anymore. Volume cannot be variable. But when it is, volume is not independent. Okay, here volume means actually, or if you fix volume, then actually the moles will be fixed. Okay, PT. So fixed mass fixed composition, 2 only, 2. As you know, it is 2 degrees of freedom. As I told you, 2 variables. For a pure substance, only 2 independent. Pressure, temperature, volume, temperature, pressure, volume, or any such thing. Now, but can it? This also discussed. The degree of freedom will be 3 rather than 2 if it is variable size, or say when this is not a fixed, not fixed. I can take. Then question: can I take with this pressure, this temperature? Yes, I can take. See, I took this temperature. I took this pressure. I took independently. This can be 4 or 5, 3 moles, or 3 or 4 or 5 moles. I can take. Then this is the difference. Then this is name of this what system is what now? It is variable mass. This is an example of variable mass. Tell me, without variable composition. Without variable composition. This is fixed mass fixed composition. Now what is another example I am giving? Variable mass as well as variable composition. You follow? Then I will start this. Yeah. This is forget about this. I am showing you. Where shall I start? Consider this is over. This place you just forget this. This is like something. Don't get mixed up. Achha, this I will return in case. Remove this. Now variable mass with variable composition. Chemical reaction system I said. Incidentally this is not. That's why this will be variable mass, any of them, any criteria, any, with or without under this system. Okay? This is the variable mass with or without. Examples are this, but a chemical reaction can not necessarily variable mass. Okay, variable mass with variable composition. It can be without. For example, here. Okay. For example, I tell you what. Variable mass. Follow. With example on I'm giving you, clarifying, okay, don't worry. Example, variable mass with variable composition system. This English is little bit erroneous, but you understand. Variable mass with variable composition. What is the example? I am taking this. Follow this. Again, the reaction is reaction under study. This is a chemical reaction system. CO gas plus half O2 gas, we follow this, is CO2 gas. So a little bit difficult though, but once you understand, follow, see how I am practically carrying out. I am trying to follow. Again, thermostat a temperature, the temperature I will fix independently. T is, I am writing 900 Kelvin. Just I am changing means to show that I am independently fixing it. Pressure, what I am doing here, pressure is say 3 atmosphere independently. What I am charging here, follow, charging certain moles of say 3 moles of CO. 3 moles CO. Tell me what is the oxygen? 2 mole oxygen. That's, you see, arbitrarily I am writing. And then 2 mole CO2. Okay, or maybe say okay, or 3 moles 2, okay, this okay. 1.5 mole maybe, okay. 1.5 mole CO2. This I have taken. See, all arbitrary. Now, why it is? This is actually the moles variable mass. Okay, sir. I can take means they go here, right hand side. See, this you test yourself. That I can take easily, independently. So, independent variable. This is the space. This is the place for the independent variable, right hand side. They can, so they may go. Okay, so that means here you can write. I am writing in the same way. So H prime is a function of state property, function of state as is right, state property. H prime here you know understand extensive. That's why moles is coming. What is this function of state is what? Right? Tell me. Temperature sir, pressure sir, NCO sir, NO2 sir, and CO2. But why it is named sir variable mass? Is a variable mass, chemical reaction system, variable mass, variable composition you have added. Why variable composition? See, you are taking arbitrary changing though. You know what is the composition here? You know composition is mole fraction. You should note that. Composition is mole fraction. Mole percent, volume fraction, volume percent, weight percent, all are composition. Mole fraction is the commonest to us. So mole fraction is what? X, I am writing. Mole fraction symbol is X. What is this? XCO is what? You know, remember forever. You know this though. NCO by N total. What is this? Tell me. What is this? Tell me. I'm just removing this. I'm writing here. T is 900 Kelvin. This. Good. So 3 by 10.5. So 3 by 10.5. Let it be. XCO2 will be 2 by 10.5. And XCO2 would be 6.5. Okay. Achha, 6.5. Right. Since I have started with 1.5, let it be 6.5. And this will be XCO2 1.5 by 6.5. 1.5 divided by 6.5. This is the composition. The variable composition, why sir? Variable composition means now follow. You variable mass change 3 to 4. Variable mass. And really, the moment for it is no longer same mole fraction. Your total has changed a 4 by. See, so 4 by, the 3 by 6.5, you will know very yourself. 3 by 6.5, note this, 3 by 6.5 before XCO. Before, in the previous case versus what is now, when 3 is 4, tell me 7.5. At the same, we believe plus 1, variable composition. Variable mass accompanies variable composition. Because they form a single phase. These form a single phase. What is the phase? Gas phase. Gases are miscible in all proportion. So this is the meaning of this. Gases are miscible. So it is also chemical reaction system. And how will write this? Again, this like this. This is example. Then this will what? This will now take up this. I will be happy if you can answer this question. Is it a variable mass? Very interesting though. This I have taken it because this is a metallurgical system. I could consider this reaction also. This reaction I could easily consider. Any reaction I can consider, but simple reaction I have to consider, and more I have considered metallurgy. But incidentally, this is chemical reaction system. But although I have said these two, but these two actually chemical reaction system, but still variable mass I have given with or without, which is certain. Variable mass, with or without. The variable mass with variable composition, variable mass without variable composition. This is the example, variable mass with variable composition. This is the example, variable mass without. Why? Sir, these are all pure stuff. You change, sir. What is the mole fraction? You ask me. What is the mole fraction? I have charged. A mole fraction, pure substance is alone, 1. Pure substance is alone, no one is there. In this phase, no mixing. Metal does not mix with gas nor with MO2, the oxide. The pure, XM is pure, right? Pure. Pure means what is in this phase, who are present? In the metal phase, what are we? Metal alone. So number of moles of metal is M, a total number of moles is 10, number of moles 10 by 10. Similarly, XMO2 is what? Tell me. Pure. Okay, this pure M, pure MO2, sorry, XMO2. Follow me. And 5O2, XO2, can you tell me again? Gas phase alone, oxygen alone. If it is nitrogen and oxygen, then this will be actually variable mass, variable, again that category it will move to. But in this case, particular XO2 is pure oxygen. Gas phases, gas component tend to mix up completely. Example, air. So many components are there. They form a single phase, namely air is a gas phase. Okay, so all gases, okay, spontaneously mix up. But solid actually limitation, solid, liquid. Okay. So now you see, now you apply. So now I will say change, sir. You change the masses, variable mass, make it not 10, 11 moles of M. What will happen? Will it change? Composition? Oh, so still mole fraction. Composition is mole fraction, so 1. It's okay? Then it's okay, happy? So this part, so with this, so what is this? This is an example of, write this. Can I remove this? Write this? Good boy. So start. So this is an example of, so this is an, right here. So this is an example of, so the reaction, again, so the reaction M solid plus O2 gas goes to MO2 solid is an example of, so the chemical reactions. So right, chemical reaction system though. So the chemical reaction is an example of, tell me, is an example of a fixed variable mass. Variable mass. See, can you take? You ask yourself, can I? Then you can write here. Chemical example, variable mass. And without. variable composition. Very good. Variable composition system. Okay, again I'm taking another example. Just I'm removing this. These are no longer needed. These are another example. Another example. Follow this. This will be another example from solution system. I just said solution system. You will very easily follow. Solutions are what? Another example. Okay. Solution system. Follow this. I'm writing. I'm taking a solution of, say, your metallurgist. You always consider this steel is a solution. In blast furnace, hot metal is a solution. Okay, slag is a solution. So solution everywhere. Brass is a solution. Okay, all these things. Okay, any bronze, all solution. Alloy. You speak of alloy. Solution means alloy. Mixture, single phase. Okay, system. What is this? I'm taking. Follow. I'm just carrying out the line right. I'm taking. And this is my system again. This is best way to explain. I am again temperature. So since it is a metal, maybe say 1500 Kelvin, okay, so 16 Kelvin. High temperature should be, so for it to be solid or liquid. What is pressure is, say, typically say 1 atmosphere. These are all arbitrary. Then I am doing what? The system is, solution system is, right, like say iron, manganese, silicon. This is the 6 things I am taking. I am writing. So, NAP arbitrarily, you follow me. Okay? This is measure 95 moles. 95 moles. N manganese say 4 moles. Just example. I'm taking arbitrarily. And what it is? N silicon 1. This is a figure. This is what system? This is solution system. No chemical reaction. Here, iron, manganese, silicon. This is a solution. This is a solution. So how will you write here? Tell me once more. In the extensive form, H prime is function of. Tell me pressure. Equal subject pressure, temperature. Right? Tell me NFE, N manganese. And don't think to me I have to make 100. Okay? It can be any value. So let's say 3. Make it 2. Okay? Anything. Don't worry. 2 moles. 2 moles. N silicon. Happy? High silicon alloy. So, still the same I write. That is, again, fixed mass, variable composition. Right. Another example, I write another example of, right, again, variable mass. Write nicely, variable mass and with, tell me, variable composition. Why, sir? Tell me. Now you will appreciate. Similarly as gas, in solution to single phase. This is a single phase. Iron, manganese, silicon, single phase. Right here, right, single phase. That's why they call it a solution. Single phase is a solution, is a single phase. Okay. See, why variable mass? You have taken variable mass independently. Variable composition. Why? The moment you change 96, 95 to what is the mole fraction of this? 95 by 101. You make it 96, then 96 by 102, not same, change. Or like this will be 4 by 101, and you make it 7 by, okay, 103, 104, such things. So, the solution is, this is not reactive, no reaction, they are purely solution. So, you have understood the whole thing here about the system. Now start our main job. Again, so remove this, start. I start now. I told you this first line, if you appreciate, other lines are easy. I am writing. dH prime. This is mathematical. dH prime is what? You know the total differential. dH prime, I am writing for you first time. T, you practice this with me. T, NM, this is math, total calculus, but you should be careful. dP plus first term, second term, dt, constant pressure, NM, NO2, NO2. Check with me. If it is wrong, let me know. 2 terms I have given, I will get 5 terms, okay? So, so what I will tell you, okay? I am removing all this, I don't need any more. These are all used. No. We have understood? This is a chemical. Plus what? plus what you write? DH prime, what? Tell me. You see, Anurag, I've written two terms for you. Are there any terms?
D is like D,
DM first, is it? The way? Systematically, DNM, right that. Temperature, what's all right here? Temperature, pressure, anything? NO2, NMO2. Okay, write that. First day you write fullest. Next day maybe I will skip some terms. But anyway, today I have to take the trouble of writing because this is the beginning lesson. Tell me NM, NO2, NMO2 times DNO2. Happy to? Good boy. Then next time you tell me, think about this. Tell me, okay? Quickly. Third last term, DH prime, yes. DH prime, you tell me, okay? Subnil, DH prime over DN. The last one, partial derivative. They call us partial derivative. Now what are the fixing? Temperature, pressure, as you write, temperature, pressure, and NM and NO2, DN, yes, total. You will understand now. As I told you, follow the difference. Chemical reaction system and pure substance system. I am writing next or DH prime PT under constant pressure, constant temperature. What will happen to the first two terms? Actually, I tell you, what is the name of this? You know, what is this? Anyone can tell me? What is this? DHDT? That's CP. Because these are constant. Try to understand the constant. Very important. These are the dH by dt is CP, NCP or CP for the fixed mass fixed composition. When you say these are constantly fixed, so you can apply the CP. And also you know dH by dt at constant pressure is CP. And yes, constant pressure standing. So CP sir. And because these are all the fixed mass, these constant applying here fixed mass. This part at least this is total is variable mass, but this term fixed. Constant means constant. What is the constant for a given values for a given when they are constant. So fixed mass return to fixed mass it is CP. But more importantly, if dt is constant, dt is what? 0. T is constant. This term drops off. And if pressure is constant, so you see, first two term drops off. So if temperature pressure constant, repeat, if temperature pressure constant, can you have any enthalpy change? Can you have any enthalpy change with this system, with fixed mass fixed composition system? Say 1 mole ideal gas, easiest. Can you get an enthalpy change with 1 moles of ideal gas when temperature pressure constant? A moment ago, two things constant means all constant. Moles constant given initially and temperature pressure, three things constant means volume constant. Means whole system is constant. So no, so there is no value 0. But here no, even though these two are 0, there are these terms. They will give the enthalpy change for the system. Okay, that is for the chemical reaction. This is pertaining to the chemical reaction. You follow that. Follow this. So this I am writing is 0 plus 0. Plus. What is the name of this? You follow this. This is a nice name. I am writing. You follow HM bar. Whole life. This is the beginning. The name is partial molar enthalpy of M. This is the convention. HI bar. I am writing here. HI bar general. HI bar is what? Partial molar enthalpy of the species I. This is the answer. Okay, so this is the name. So write nicely. HM bar. I am writing with you. HM bar DNM. Then what is the name of this? Tell me. Similarly, you have no No doubt HO2 bar, and likewise I am writing here beforehand HMO2 bar. What is this? What is this? Yes, Nirjo, what is the name of this? Partial molar enthalpy of oxygen. Don't worry. Looks gorgeous. Molar. Molar means 1 mole enthalpy. Molar enthalpy you already know. Enthalpy of 1 mole. It is partial. Why? Tell me. Partial is general. Partial is applicable when there are other components in the same phase. In the same phase, there are other components. For example, a moment ago, iron, silicon, manganese, they are partial, very easily understood because it is solution, sir. It should be a solution, partial we apply. In fact, this pressure here, oxygen pressure we see in the air, partial pressure of oxygen, not pressure of oxygen. Why partial? So there are a number of components. Total pressure is 1, but partial pressure of oxygen is 0.2. Okay, why partial? Don't say pressure of oxygen, partial pressure of oxygen, because there are nitrogen also, there are moisture, carbon dioxide, inert gases, so many gases. So partial. So that's why I say partial. So a number of things. But later on you understand in this particular case, it is partial does not apply because this is a pure phase alone. So partial, but generally speaking, go by generally say general. Partial, then the moment you will see it is not partial, it is pure, then there is another symbol I will use called pure, molar enthalpy. It becomes molar enthalpy of pure. Generally partial, insist on this and then follow me, right? Then next term will be, tell me, HO2 bar, DNO2 plus HMO2 bar, DNMO2. Quickly, now go fast. Now you say no, now, so this is out. So what you are getting? Now let DNM is the negative. Minus DNM is minus DNO2. You check this. What I am writing is plus DNMO2 is DN. Say is DN. Say follow this. What I have written? Check. Don't worry. From where? How do you write, sir? From stoichiometry. From the stoichiometry of the reaction. From the stoichiometry of the reaction. What is the stoichiometry? Means how many? 6. What is written? I have written stoichiometry 1:1. This is the stoichiometry. Remember, this stoichiometry means dispel any confusion right now. This one apply for the extent of reaction. Means when 1 mole react out, 1 mole of M react out, then 1 mole of oxygen also react out, and 1 mole of MO2 will form. It does not mean that I have to take 1 mole of MO2. I have taken what? How many moles? 10 moles, 9 moles, 7 moles, etc. So okay, don't worry about this. This I may take, but that means this one is a change. Stoichiometric coefficient is a change. Dn is the number of change in the number of moles of M is what? Whatever it is as much as same, as much as this. When it is 1, it is 1. When it is 5, it is 5. This signifies that. Similarly, when it is 1, it is 1. Signifies that. These 3 things are same called Dn. Okay, for convenience. Okay, say. Remember this. Okay. So remember here. Dn, these are changes. Change. Why change? Why change and why minus? Yes, Somo. Why change and why minus? Change. Why change? Decreasing. That's why I have given minus, so make it positive. This is a positive. That's one answer. Correct. Why change I am considering? Why not Nm? Why not Nm? No. Change, sir. Reaction causes change in the number of moles of reactants according to the stoichiometry. So changes, these are verily the changes. 1:1 change. So right? These represents 1:1:1 are the changes in mole rather than the absolute mole. No. Rather than the absolute number of moles. That can be anything, sir. No connection with stoichiometry. It can be 10, 7, 300. It can be anything, sir. But the reaction, the reacted, how much reacts? Follow the stoichiometry. So changes in the number of moles of M. So good. See, NM is one thing, DNM is another thing. NM is number of moles present, DN is a change that has occurred. They follow the stoichiometry. Okay, so this I should actually remember, always careful. Your high school, this is not you may take 1 mole, etc., but you may not take anything. You may not. You normally don't take product. You will take. So that is free, but you are not free here. It is bound by the stoichiometry, as I have written. Okay, so now complete this. I remove this line. I remove all these lines. All these lines. All. Now start here again. So dH prime pt or dH prime pt. Do this. What is this? This 0 out. So you please, I am writing, you can check if I am correct. HMO2 bar minus HM bar plus HO2 bar plus give a second bracket, maybe another bracket, not bad, DN. You are all set, no? Is all set, huh? Correct? Check. Yes, I think you are correct. Okay, DH prime PT. So again you see, as I have already said, constant pressure, constant temperature, still a process occurs because it is a chemical reaction system. This is actually famous delta H. This is famous delta H. So delta H is where delta H is. Write nicely here. I am giving you another HMO2 minus HM bar plus HO2 bar. So it is called H of is sigma H products minus sigma H reactants. Sigma H reactants. Product is the only one. So generally it is product. Sigma product. This is this whole thing. This is. Okay. So this is reactant. This is the product. Sorry, product. This is product. Reactants. So you are here. So delta H. Okay. This is also what is the name of this? This is I am writing right here. Name is enthalpy, or more popular enthalpy. Acha, I'm writing heat. That is enthalpy. Heat is popular. That's why I wrote enthalpy of reaction. Heat of reaction. Enthalpy change for the reaction. Okay, this you follow this much. Okay, this is. So I am writing this. What I write nicely? Tell me delta H, the heat of reaction. So heat of reaction I will take up next, but I have introduced already. Delta H times Dn. Tell me. How interesting. I will be very happy if you can answer what is this. Can you tell me what is this? Or you think about this, I will ask you. I mean, integration. So do the integration. I am doing the integration here. Shall I? Or take another step? Maybe. Not bad. Integration. And this is integration delta H dn from state 1 to state 2. State 2 is, what is the state 2? Sir, you do one thing. State 2. Yes, after reaction, moles will change. Okay, this will take up again. So state 1, starting. 10 moles, 5 moles, 3 moles. Then after reaction, some 10 is 9 down, 5 down, 4. O2 will be up by 1, etc. It can be. So it actually depends. So 1 to 2 delta H from initial state to final state, right? Initial to final. Shall I give you this example? What is initial and final? This I'll give you example. You will follow. What I am saying, for the time we consider is delta H outside, taking outside. If it is independent of dn, this is interesting. In this case, valid. In this case, valid fortunately, because which is this? This is not partial anymore. This is pure substance. So molar enthalpy. Molar enthalpy does not means pure 1 mole enthalpy will change whether it is in association with others. Because when it is changing, when the mole fraction changes, then this value depends on mole fraction. So mole fraction don't change whether 5 moles I start with, it becomes 6 moles. Like this job. Molar value, molar enthalpy of this at 1 mole does not change when it is greater. 1 mole value remains when it is larger number of moles. Okay, reduce. Okay, it becomes smaller. 1 mole value is same. So this is actually, remember, 1 mole enthalpy does not change. See, with the reaction, progress of the reaction. With the progress of reaction, what happens? Moles change. But 1 mole value, 1 mole is what? That's the character of this substance. Okay, so MO2, 1 mole MO2 enthalpy is what? What is enthalpy? Internal energy plus PV energy. So go back to this. Internal energy is what? Translation, vibration, rotation, all such things. Okay, so enthalpy, 1 mole. So although bar, for generally speaking bar, but it is actually for pure substance. Another name is there. So it will suffice to say that this is, in this particular case, is not varying with the number of moles changing. Why it is changing? Why Dn changing? Why Dn? With Dn is what? Change in moles. Dn is NMO to all. So why changing? Why changing? Why it should change? Yes. For the sake of
Reaction.
well, reaction occurring, sir. Who else will change? Reaction itself changes. I could have taken away something. We could have. That is another issue. Here reaction is changing the mole. So Dn represents that. So delta H times Dn 1 2. Then if if delta H is constant, is not function of is constant, right? It's okay. It will not change. This is possible. In this case, it's particularly possible. That's why I've taken this example. So what it is then? Delta H. Tell me. Delta. Good boy. Number of moles that has changed. Okay. And what is this? What is this? Or right here, or this is, tell me, 1 to 2 means that dH, any integration dH is forever delta. Delta H prime Pt equals to this box, verily. Happy? Okay. So, unless I sketch this, it is getting difficult. I'm quickly sketching this, starting. So, what is the pressure? Fixed pressure. This is temperature. You know the values. You know best. What is right? Arbitrarily, randomly. MO2. Okay, and no link with the stoichiometry here. Okay, but you can take stoichiometric amount. You are free. So 10 m, 3O2, 1 MO2. I have taken. So this is state 1. Initial state. What is the name of this? Initial state of the system. What type of system? Chemical reaction system, sir. So these are unnecessary now. All unnecessary. Initial state. Now see, it progresses to the next one. For example, suppose one. I tell you. Say suppose this reaction will take place at this condition. Let it occur. Temperature. Okay, what will happen? Suppose 1 mole. We go step by step. 1 mole, 0.1 mole you may consider. Anything you may consider. Suppose 1 mole. 1 mole and react. Reaction is given. 1 mole react. That means what is the corresponding change in the oxygen? 1 out. And 1 gain in the MO2. So write this. Say 9 m, good boy. 2O2. 2 MO2. 2 MO2. Okay, not 1. 1 already there. So 2 MO2. So what is the delta N here? Delta N is what? What is the N? Is 1. 1. So if it is 1, I'll ask you questions. Is delta H. When? Nicely. Delta N is 1. Achha, when delta N is 2, 2 means I'm writing along. Can I write alongside? So alongside. When 2 means how much it is? 8 m. How much it is?
3.
No, 2. 1 O2, good boy. 1 O2, 1 A2, and this will be 3. Second case, what is delta N? Is, tell me, is, right? I should write here, is 2 delta H when delta N is 2, and similarly 5, 6, 7, 3.5. No problem. Now, you consider simplest case of, you understood this, that is the cardinal thing, most essential. So first follow this. Delta H prime Pt, let us get back. I'm writing here. This only this much I'm picking up. Consider, just here, this will be good enough, but very important lesson. And I asked you that question, you have not answered yet. Follow. This is the important question. What is this? What is this? Tell me. I don't want anything. Then it will be all set. Heat of reaction, all these things. Delta H, Anything you say, any one of these two, any will do, or maybe both. I want actually both. What are they? As your knowledge, as per your knowledge, you have seen everything here. Say this is the picture, this is the reaction representation, and this is the this. So the first case, okay, one moles, okay. So what is this and what is this? At this you can tell. A moment ago I have written there. I have removed this heat of reaction. This is the delta H, na? Heat of reaction times this enthalpy change. Delta H is what? This gentleman is delta H. H written here. This is your enthalpy of heat of reaction, right? This is your. I'm writing for the time very popular heat of reaction, but heat of reaction. Now see, as I tell you, when I started, I found that suddenly heat of reaction is very important. A moment ago, when first law of thermodynamics, ideal gas, adiabatic, constant pressure, constant temperature, they are talking about system. Delta U system, delta H system, Q, W, very good. But suddenly, after this, entering into this chapter, thermodynamics, they always talk about heat of reaction. But why is the system gone? We have to follow one pattern: system, surrounding. System, since we are actually considering. So what is the delta H system? You got the answer. You got the answer. Sir, this is the system change. This is a certain H prime. I told you, H prime is a function of state. Write that once more if you have forgotten. H prime pt is what? It is a state function. Is what? Function of state. And that that state actually I have removed all this place. Okay. See, remember. So this is the system, sir. H prime pt. Enthalpy of system is what? First line. Return to the first line. Shall I remove this? Yeah, good idea. Follow first line. Recall the first line. I have to do this. Recall the first line. Why? See, then you understand. Oh, system. Yeah, reconcile, sir. Happy, sir. Oh, heat of reaction. Enthalpy. All reactions are as much as you like. That is actually the system enthalpy change. You will get system enthalpy change where? Throughout ideal gas. Also, adiabatic, constant pressure. All delta, the least table. Delta H is what? Enthalpy change of the system, 1 to 2. Delta U, 1 to 2 system, internal energy change. Q, heat interaction between system and surrounding, 1 to 2. And likewise W. So you are said here. Suddenly, if you actually your mental pattern is actually disturbed, then you will find no logic and you start memorizing. And subject is of no interest then. Okay. But this is actually, because the first line is what? As follow. I wrote somewhere else, but I am writing here H prime pt. I am very sorry. H prime. Initial is what? State function. First test class. State function, path function. First state function. I know function of state. What is it? Is a function of, say, PBT, etc. But first line is a state function, is function of state. And state is represented by something. And moreover, this side will be independent. That is independent only. No independence. No. This side independent. Function of state. Then you write what state is given by what? Tell me in this case. Tell me. Pressure, temperature. Then you ask yourself, I am writing, can I independently fix? Sure, can I independently fix? Yeah, yes, I can. Take any temperature, any pressure. No, who will stop? Name. Good boy. That's it. Nothing else. Nothing else. Okay. So what is this function? This is the state property. Function of state. Okay. Okay. Enthalpy of system. H. Enthalpy of system. State property of a system. State property of system. Look at enthalpy of system. Okay. So you write this is the enthalpy change. This is what then? Enthalpy change. Change. Tell me of the system as it. Tell me as it moves from state 1 to what I don't write. State 2 final. See, unless it is 1 to 2, you are not satisfied. So what is 1 or 2? You are previously very nice, sir. Go back to ideal gas and don't teach more. This is suddenly this one, the next day you say still another one. Consistent, sir. Consistent. One principle, sir. Whole thermodynamics, sir. One, can you do this? Then teach us. So state 2 is what? Oh, final state. The right final state. Happy? Okay, good, very good. So, as the system, yes, you gentlemen, Devapam, as the change of the system, as it, the system, moves from one to state. Then delta. Then delta, still another one you write here. I will tell me. See, explain number of ways, write number of ways, think number of ways, dream number of ways. And then I said, sir, no. Oh, Papa, I will not do. Don't try to be scary and trying to avoid it. Okay? So. I'll ask you again. Here, another one. As the system, right first, as it moves from state 1 to state 2. Very bad. I actually run into actually in a scarcity of space always. I just 1 to 2 in the figure, shown in the figure. Still I'll ask you, since I've asked him, till another way. Sir, what is this? This language, this is in mathematical form. From this. You already did. Okay? What is this? This is delta. I'm helping you. Delta means change. Delta means change. D is a change. Differential, sir. This is integrated, sir. What is change? Then it should be a change. Means minus. Something minus something. Can you tell me now? I've actually giving you a head start. This is very easy for anyone. One final minus initial. Delta H is what? Your ideal gas expansion. Here you see, radiative. Delta H 1 to 2 is what? H2. H2 of what? Of system. System at the second state has this enthalpy, gentlemen. What value it is? I don't know, sir. Please don't ask about the absolute value. We are thermodynamics, we use normally changes. But the meaning is that final absolute minus initial absolute. That is no doubt. In some cases we know, for ideal gas we know the absolute value also. But that is very simple system though. So what you write this as? Tell me, therefore, HPT final means state 2 minus this means as a writing separately, I'm writing separate. I'm giving arrow here and then for here. That will be good. Note delta H prime PT is H prime PT state 2 means final state. Sometimes state 2, sometimes final state. It always happening. Initial final. This is my final. But why final? If you can go further, so let it consider. I have considered up to this stage. It can go. What extent it will go? That is different subject. That is different issue. Equilibrium extent. They go up to equilibrium. That is after the second law. What is the equilibrium state? Whether different issues. Don't do. But for the time up to this extent. So yes, where I am writing state 2 or 1. Final minus state 2 means final, right? You follow the same convention, same pattern. Minus H prime PT state 1. Okay, this is the meaning of this. Okay, this is absolute enthalpy test. Okay, over this part is over. So now I take it formally. This is over. Actually, I don't have to. You can get this. You get this. Okay. No, these are now something additional, simpler thing. Note delta H. This is what delta H prime. Delta H. Okay, heat of reactions. I'm writing heat or enthalpy of reaction. Please tell me. Is positive means, can you tell me? Let us see. Positive. What is the meaning of this? Tell me. When? Right, it is positive. It implies when, tell me, yes, H of product means MO2 here. H of product is positive means product minus reactant. Product is greater than sigma H reactant. Then it will be product minus, then it is positive. Very good. What is meaning? First it is positive means what is this? More about this. Delta H, this delta H. Positive means you can consider in a sense this is also positive. This is exactly same, already 2 times, 3 times, 4 times, etc. 4 times positive. Delta H positive, why? Go HMO2 minus, product minus reactant. So positive means what? Product Product has more enthalpy than the reactants. Products together has greater enthalpy than reactants together, sir. Then delta H is positive. Very good. If this is so, sir, is positive, what is the implication? Delta H positive means, you can tell you, that means delta H prime PT is positive either. Is positive either. What does it mean? I am gradually taking you. Is positive means what? You have to one principle, same principle, all principle. Under constant pressure, what is the enthalpy change? Under constant pressure, what is the enthalpy change related to a measurable quantity? Heat. Q sir, heat interaction, sir. Delta H is Q, sir. Because under constant pressure, temperature is there, don't worry. Constant pressure means constant, no non-mechanical work. There is no question of this. So is what positive means either, what I have written is positive, either certainly is positive, either, oh, it is positive either, okay, positive, it is positive too, it is positive too, okay. What does it mean? This means under constant pressure is Q is positive, right? What is Q? Heat interaction, sir, between system and surrounding. Who is the surrounding? Who is the surrounding here? Thermostat. Who is the system, sir? Where actually MO2 are there, sitting. They are reacting. They are reacting species. That is, Q is positive because right. Remember, recall. I am giving you a clue. Delta H prime. Don't worry about that. Main thing is under constant pressure is Q. It's okay. So this is heat interaction, right? Heat interaction between system and surrounding. Okay. Then further, what is positive means then? Q is positive. What does it mean? Q is positive, I told you other day. Q positive, Q negative, didn't I? When I introduce W positive means? Because, let us see. If you have forgotten, you just complete this. You complete the, too many chalks are used up today. Okay. You complete this. In case you have forgotten, please follow. Q positive, W positive. Q and W. W positive means I told you. No, constant. Don't this. W positive means work done by the system. Work done by the system, positive and expansion. You write expansion. So positive, work done by system. Work done by the system. On the, which you don't say but implied on surrounding. On the surrounding means external load. Happy to? Q positive. And W negative means, right, complete here. W negative means work done on the system. This I said. Never drift from this. Acha, remove this. Acha, here Q positive means what I told you. Q positive is what? Remember, heat absorbed by the system. Absorb. Heat admitted. Two ways you write. Admitted into or absorbed into or absorbed by the system. Acha, into the system. Let me write. Into the system from where? It admitted into the system gets it, absorbs it from the surrounding. From the surrounding. Happy? Or all right, or still you write. The negative is okay too. Negative over here. Or heat admitted, sometimes we use heat absorbed. Whichever suits you. Or that is heat absorbed by the system. Heat absorbed. Both we use, that's why I am writing both. Happy to? By the system? Okay. Next is negative. Negative tell me, accordingly tell me. Acha. This is also called, this is also very good. Tell me, negative is what? Heat admitted into heat withdrawn from the system. Withdrawn from the system to the surrounding, or or tell me that is heat rejected. Heat rejected. Absorb opposite is rejected by the system to the surrounding. Heat rejected by the system. Now another term I am adding today. Since you know this, as if you know this or you knew this, then I'm here. Q is positive means then you understand everything. This is known as, what is this? Q is positive means heat will be entering into the system. Q is delta is positive. Q is positive. Q is positive here. When heat admitted into the system, heat absorbed by the system. This is called endothermic. The new name, endothermic reaction. For reaction, we use the term, since this is about the reaction, okay, related to the reaction, endothermic is endothermic reaction. Okay, so what we say, Q is positive is endothermic and Q is negative means, tell me, negative means when negative when, right here, when Q is negative when tell me, opposite, sigma H products is less than sigma H reactant. Is negative, so that is exothermic. Okay. Why this happens? Tell me quickly. Why exothermic? This is system is moving from where to where? Negative word means this has a lower enthalpy. Higher enthalpy to system is going to lower enthalpy. So this is lower enthalpy system. Product is less. So higher enthalpy here, 1 mole. Higher enthalpy to lower enthalpy. Both are part of system, reactant product, but some have higher enthalpy, reactants maybe, some have lower enthalpy, products maybe, or the opposite. So system is moving from low enthalpy to high enthalpy. Means what is that low enthalpy to high enthalpy means delta H is high, too high, 2 means final, so delta H is positive. Positive means endothermic. Delta H positive means Q, constant pressure. Q is endothermic, and this is exothermic. Okay, means why it takes? You can answer this. Why the system takes its endothermic means it absorbs. Why it takes? Because heat is going from a low enthalpy to high enthalpy. So some support is necessary. Surrounding gives that heat. So it is endo, it absorbs. Happy? And opposite is, this is actually high enthalpy to low enthalpy. So it rejects. So that is actually, so system moving from high enthalpy state to low enthalpy. Okay. So rejecting to the surrounding. Okay. This part is very much satisfactory. I think I will not discuss anything. Acha, constant pressure. So 2 ways. How many? Hello? Huh? 20. 2 ways to represent, this is very important, to represent constant pressure. So remove all this, this over. I will draw phrase. I'll draw phrase to follow this. Draw phrase. Two ways to represent constant pressure, constant temperature reaction. Constant pressure, constant temperature represent a constant temperature, constant pressure chemical reaction. System. I am giving you first one. Two equivalent ways. Two equivalent. They're same. One is closed system. One is closed system where the reaction will take place. Another is closed system, or what is this? Closed system, batch reactor. Okay. This is actually flow system, flow or continuous reactor, flow system. Or you write another way, or continuous reactor. In the language of reactor, continuous reactor. And what you write here, another name, the closed system batch reactor. Batch reactor. You know everything, don't worry. There's nothing new. Closed system, you know, you are used to close. I'm writing. What is the example of closed system? I'm writing. Closed. This is a question that I were discussing so far. Closed. Closed system. Pressure temperature is under constant. Constant pressure. So this is the temperature. I'm not mentioning what temperature is the temperature. T say 1000 K say this is the pressure is 1 atmosphere say means it is not fixed anything. Then I'm writing how the chemical reaction here chemical reaction system in ideal gas. So what you write 10 3O2 just randomly I'm writing 3O2 and 4MO2 okay 1 okay 2MO2. The reaction is reaction under study is let me write reaction under study. Right here, top. Reaction under study to help you under study. The same is M solid plus O2 gas goes to MO2 solid. So this you understand okay, here. The reaction will occur here M plus O2 right here goes to MO2. This I am not state one I am not working. This is the system. Or this is what system? This is closed system. This is the batch reactor. This is continuous or closed system. This is more important. This is more important in surprise. This is very practical. This we use, but this we will use more. Okay. So what is this? How you carry out this experiment? Follow me. This you have taken metal sitting in a container called crucible. Crucible metal powder. Metal powder, right? Or solid metal powder. Achha, this is a furnace tube. What is this right here? Furnace tube. For example, furnace tube. Tube furnace they call it. It is made of alumina, silica, refractory. And what is this? This is the temperature or this is a furnace. This is the furnace. This is the tube. This is the furnace. Furnace. There are different kinds of furnace. Okay, silicon. What is this called? Canthal. Heating, the nichrome heating and so nichrome not canthal or say silicon furnace. Okay, don't worry. Heating element may be there. This is the heating element. This is furnace, and with temperature controller. What is the job? Yes, fixing constant temperature. Right? See constant temperature thermostat? No, sir. Controller. Controller will fix the temperature. To fix the temperature. Then what it is what is entering? Flow reactor. Flow reactor. What enters gas? Oxygen gas. Oxygen gas is flowing into this metal and gas leaving. Oxygen leaving. Okay. Some oxygen leaving cells. If there is unreacted oxygen, if any. Unreacted oxygen leaving. Okay. Metal here, what you will get here? Yes. Yes, you tell me your name. You are actually forgot your name. You are Somu. He has come. What is his name? Vidyut. Vidyut will tell us what you will get here. Sir, yeah, I have time for 5 minutes. 5 minutes have passed. What you will get here? Now, species will do. M and M2. Some M may be still not reacted yet. If it is react out, then fine, it is gone. So M and MO2. After this state 1, state 2 maybe. Don't do it like this. But oxygen will not be confined here. This is leaving. The gas stream leaving. Okay. So this is equivalent. These are two equivalent. Remember, equivalent. So this is constant pressure temperature. Constant pressure temperature. Don't worry. We will consider both of them. Okay. But this actually in the same line as the ideal gas system. Okay. So system here previously it was ideal gas. Here is chemical gas system. So over. Second is quickly. Now I tell you what I tell you. Okay. Follow this. Some additional features of thermochemistry. Additional features. Oh, sorry. No. Coming to important things coming. Heat of now start. Formally, heat of reaction. Already I have introduced, so no problem. So can I remove this? Achha, right. Let me heat of the start. Next take up. Next take up. Take up means you understand that I am taking up. Heat of reaction. What is this? What is it? Enthalpy change. Heat. 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 I prefer the term enthalpy. You will be surprised to hear. I prefer myself personally prefer the term enthalpy because enthalpy is reliable. Why reliable? State function. It is not deceitful at all. But Q is a path function. Okay. But in this case they are same, exactly equal. But still actually we feel very comfortable with delta H. But under constant pressure they are same. It does not matter. You can interchangeably use this. But still I tell you. That's why I often add, people say heat. I don't like enthalpy is the trick. Enthalpy if you see H2 minus H assigned to the state, enthalpy, state property. Q is actually no interaction. Heat of reaction is heat or enthalpy change. This is the associated with quickly some discussion, then I will perhaps stop, then I'll take up next class, maybe the remaining, hopefully. Associated. Now main difficulty is over. If you follow these conceptual things, then it is over. Okay. Then the rest is enthalpy associated with the heat enthalpy associated with the chemical reaction. With the chemical reaction, you understand? Occurring taking place at a occurring at a constant pressure, constant temperature. Temperature is very important, and constant pressure. This is the constant pressure. I am not writing pressure, constant pressure. This is actually the definition. Now, three types of heat of reaction. What is this this underline. This always you see always coming. Constant temperature at a given temperature, constant temperature, fixed temperature, always no one can escape. And enthalpy change. What is the three types of heat of reaction? Three types of heat of reaction. HOR, heat of reaction. Same time. One is heat of formation. Heat of formation. I'm writing heat, but remember enthalpy. You may use enthalpy like me. Enthalpy change. Heat of formation. Quickly. Second is, tell me, heat of combustion. Combustion is fuel combustion. You are studying fuel this semester? Are you studying fuel combustion this semester? Okay. Third is what? What? Heat of solution. Solution thermodynamics. These are the things, okay? Heat of formation. Now I'll take up one by one and then remove all this so that this is now clean quickly. Heat of formation start first. Heat of formation. Very important. Just follow some. So why this happens this day today? Talks actually now consumed like anything. Achha, heat of formation, enthalpy change, tell me. Heat or enthalpy change. Again, same. Heat or enthalpy change. I'll stick to this. Enthalpy. T. Enthalpy change. Heat heat or enthalpy change. Achha, heat interaction. Heat interaction or enthalpy change. Better. Then when important. When one mole of a compound. When 1 mole of a compound is produced from it constituent elements at a given temperature and pressure. Again at the end like a refrain, at the end same refrain, same line repeated at a given temperature and pressure. Why this? Why temperature? Because temperature, enthalpy is a function of temperature we have seen initially, and pressure. So enthalpy of any pure substance and they are participating in a chemical reaction. So no surprise, heat of reaction will be a function of temperature, but we'll see. We'll see how much it is. A good boy. I got one. So enthalpy change. So start. Underline. Never ever. Right. Never. I don't write. Never ever forget. Underline. At a given temperature and pressure. That's it. Okay. So example. E.g. I'm writing. Follow me. Follow with me. Easy. First I'm writing. M solid. Your example goes to MO2. Is it a formation reaction? Example of formation reactions. Number of I'll give you. Example of formation reactions. Formation reactions. I'll give examples. This is it satisfying? How many moles of compound? This is the constituent elements. 1 mole is produced. From it constituent element at a given temperature and pressure. So Tp. How do you represent this? This is all a heat of reaction. Generic name is heat of reaction. All heat of reaction. But this is special type where a compound is formed from the constant element. What is this? This is actually known as formation. How do you write? You follow with the idea MO2. This you write subscript the compound, the product, right? And then what you write? Temperature, pressure. Say like the temperature may be 300 Kelvin, say 500 Kelvin. Pressure may be 2 atmosphere. Say you write accordingly. Say, but this is the convention. What is the convention? Delta H MO2. This is the formation. Enthalpy change. This is the delta H heat of. This is your heat of formation. This is the symbol for heat of formation. Heat of formation. Okay. Quickly, I'll ask you. Then next in a hurry to take up number of formation. More examples. Continue from here. It is better given this. Continue. More examples. Quickly finish. I am interested in M2O3. I am interested in say Ap2O3. Now I am not considering M symbolic. I am giving realistic. Ap2O3 is the ferric oxide, the hematite. Ap2O3. How you write this reaction for this? How you write the reaction? What is the formation reaction? This is the formation reaction. Can I write here? It's an example formation reactions. So more examples of formation reaction. Yes, good. Formation reaction. Write this in case you have difficulty. Yes. 2 Ap good plus. It can be solid liquid later on. Don't worry. Run one by one. 2 Ap plus 3 by 2. Correct answer. Are you following this? It cannot be otherwise. 1 mole of a compound. Constituent elements iron, oxygen. Element means you understand periodic table. Periodic table elements are there. So O there, O means O2 here. Okay? Fe plus O2. Okay, 3 by 2. Then you say another one. You tell me. CO gas. Yes, one of you should say CO. Nirjor will tell us CO. Vidyut tell this CO gas. Carbon monoxide gas. What is the reaction? This I want to form. Heat of formation for CO. C solid. C plus. Good boy. Very good. At the last, since you are doing well, so Ap3O4. What is the reaction that should be considered? Ap2 gas. Okay, gas. 3 Ap. So it is better now. Actually, I give you the sign. Okay, Ap2 solid. This will be important. 3 Ap solid plus 2O2 gas. Okay. How the symbol? Tell me what temperature, pressure. Suppose I am carrying out this reaction. Say 800 Kelvin. 800 Kelvin and 3 atmosphere. So how do you write this? How write delta H Ap3O4 300 Kelvin 3 atmosphere 800 Kelvin 3 atmosphere. Okay, very good. So you get this. Now another last one. I'll ask you. Last one. You can do this. I see. Good. Very good. Last one is calcium carbonate. Chosen calcium carbonate, which is a limestone. Okay. Calcium
CO plus CO2.
CaO plus CO2. Solid plus gas. Is it okay? Everyone, with everyone? Huh? Follow the definition. Then you see okay or not. 1 mole is correct. What is give? Oh, another underline I forgot. Form its constituent elements. Underline that also. Underline that. Go back and underline constituent elements. Does it satisfy? Is it satisfied here? Vidyut? Is it satisfied? He has said calcium oxide plus carbon dioxide is satisfied. Constituent elements? No, sir. What should be? Calcium solid plus carbon solid. 3/2 O2 gas is calcium carbonate solid. This is the answer. Okay, you correct though. Okay. What are you doing? Playing with this or saving? Okay, this is okay. Next is now interesting. Concept of standard state I have to introduce here. No way. Concept of standard state. Concept of standard state. Okay. Concept of standard state. Remember, for solids, this is very important. Whole life. Concept of standard state is what? Pure state. Pure state. Pure substance. Called for solid, pure substance. Pure substance at 1 atmospheric pressure. At 1 atmospheric pressure. And at the temperature of interest, and at the temperature of interest. For liquids what? Same. Pure substance, same, ditto, same. Okay, pure substance. And for gases, okay, you can say pure oxygen, pure gas, again at 1 atmosphere and at the temperature of interest. Right, again once more, temperature of interest. Note. Okay. So I am writing again formation reaction. So get back to the formation. So consider the now considering the reaction M solid plus oxygen gas is MO2 solid. This is pure substance. This is pure. Okay, and this is also pure oxygen. Then what is this? This is known as, how do you write this? HMO2. HMO2. Tell me what do you write at temperature pressure? TP. You write TP. Is what? I tell you what. Since it is 3 minutes. TP is what? HMO2 is actually, how will you write this? TP is 1 atmosphere. Then what will call this? Follow? T1 atmosphere. We carry out at 1 atmosphere this formation reaction, but there is a temperature, there is a pressure. Temperature is T. Pressure is, I have considered for some reason 1. See, then it is satisfying the requirement of a standard state. So that means this heat of formation. This is the heat of formation too, or enthalpy of formation. Heat of formation or enthalpy of formation is as good as standard heat of formation. Delta is 0. Okay, right? Similarly, right? MO2 T. Right nicely. What is this? Standard. Superscript 0. known. This is superscript 0. This is superscript 0. Superscript 0 is delta H 0. PT, it is standard heat of formation. Tell me, standard heat of formation is what? When it is heat of formation. Standard heat of formation is a heat of formation. Only when the reactants and products are at standard state. Okay. So right here, standard heat of formation is the heat of formation when the reactants and products, write nicely, when the reactants and products are at standard state. At standard state. Sorry, I'm tired perhaps. Are at standard states. You know the standard states? You remember what is the standard state? Liquid, if it is liquid, it should be pure liquid. Okay. Okay, pure liquid. So above 0 degree centigrade, what is the standard state for water? Suppose this can change though, but you can initially open this. And before above 0 degree centigrade, what is the standard state? Liquid water, pure liquid water. And below, pure solid water, which is ice. Okay, these are the above melting point of iron. What is the standard state? You may consider the liquid iron. And then below solid iron. But then again, it is a matter of choice though. Later on we will see the complexity. We may consider that, okay? Though it is a standard state is a matter of choice, but for the time. This is called conventional standard state, right? This concept standard state. This is right here. What do you write? These are conventional standard state. Conventional standard state. Standard states, or you write here Raoult's standard state. Raoult's law, Raoult's standard state. Later on, you come across another standard state, Henryan standard state. Later on, alternative standard state. But this is the conventional, commonly used. We'll use this for the time being. Okay. Okay. When the reactants, standard heat of formation is the heat of formation when the reactants product at standard state or at standard states. Okay. Okay, happy? Very good, very good, very good. And heat of formation. So, actually, tell me one thing. Have you noted? I am not giving pressure here. Note clearly. See, writing this, then I am writing this. Pressure is 1 atmosphere I have considered. This is T1 atmosphere pressure. This is the heat of formation at temperature T and pressure 1 atmosphere pressure. Then I have suddenly written T, I have dropped P. Is it okay? I have dropped P, yes? Somo, I have dropped P. Can you guess why? Because I have, this superscript 0 means standard state. This is the standard state, superscript 0 to represent standard state. Right. To represent standard state, 0 to represent represent standard. Okay. Earlier, this will do. What is this? Why I am going to drop? Because standard state means 1 atmosphere mass. What is the standard state? See, underline. 1 atmosphere. Temperature of interest, what does it mean? Flexible. What T? T, as you like, 500, 600. So that's why T must be there. So this is the format. Very important. Heat of formation is very important because we use, consider heat of reaction in terms of heat of formation next class. This is the one that I wanted to tell you. Just 1 minute, just allow me, I wanted to tell you one thing. Concerning pure substance, concept of standard state. Before I leave today, this will be read. Next. Maybe I forget actually. That's why one small thing. Recall just one or 2 minutes. Recall. Some additional note it will be helpful for you. Note on effect of pressure on enthalpy. For a tell me for any pure substance, that is fixed mass fixed composition for any pure substance like metal, iron. Okay, I'm giving you. Tell me what is the relation? Can anyone tell me? Effect of pressure means what is the implication? What is the implication? Constant temperature. Otherwise, it will be effect of pressure and temperature. It implies when I'm studying effect of pressure means other variables which could possibly influence are kept constant. Otherwise, how you study the effect of pressure? If temperature also changes, it will be effect of pressure and temperature at a given temperature. Shall I write? At a given temperature, at a constant temperature. This is writing for you, but this is implied always, remember. Okay. So, what is this? Del H by today. Okay, due to 1 minus alpha T is okay. How enthalpy changes with pressure and the constant temperature? This is the answer. Quickly note, and you also try to remember. This is what? Tell me. This is known as molar. Tell me, volume. Small for molar gas, smaller volume. I'll tell you. Small for solids and liquids. You know. 1 mole volume, for example, 1 mole of water. Water, there is water. 1 mole of water, what is the volume? What is the volume? 1 mole water? You know very well. 1 cc weighs, 1 gram weighs 1 cc. 1 mole means molecular weight, means 18. So 18 cc is the answer. So what is the molar volume for liquid? Is 18 cc, or ice is slightly okay better, maybe 20 thereabout. In contrast, what is the molar volume of gas? Say ideal gas, any ideal gas, 1 gram mole volume, 22.4 liter, 22,400 cc. Of course, temperature pressure dependent, at 1 atmospheric pressure, and 0 degree centigrade means 273 Kelvin. But anyway, you have got an idea. It is 22.4 liter means 22,400 cc against 18 cc. Have it compare? Small. If it is small, then what is your comment for solids and liquids? This gentleman is small. Always for this factor. So comments. Is del H del P, right? For solids, del H by del P. I'm writing in the top. Saves time. For solids, small. For liquids, tell me, guess, solid, small. Solids is, it means volume is less, na? Liquid has greater volume too. For any, water is exception, but anyhow is small. Remember this is very important observation. For real gas, then what else? Oh, for what? Liquids, small agent. For this reason, this underline here. B into 1 minus alpha that's what 1 minus alpha T will not, okay? B matters. For real gases, I'm keeping it, okay, for the time being blank. For ideal gas, I will be very happy if you, for ideal gases, yes, you tell, you are tired, seem tired, but you should answer. For ideal gases, this gentleman, this is the question. For ideal gas, say 1 mole of argon. Or 3, What is this value? Del H by del P at constant temperature is what? 0. Because today I have done this. Alpha is 1 by T. Oh, good. So 0. So it is small, and this is 0. That means we can very easily conclude that this is an intermediate stage. Okay, real gas always is also. So between small and 0, what is the answer? Small, negligible. These are all small. Oh, প্রভাস বাবু এসে গেছে না? ক্লাস আছে তো? প্রভাস, ও কটা বেরিয়েছে? ও আমি ভুলে গেছিলাম একবারে ভুলে গেছিলাম। ওকে, I'll start from this. Hey, stop this. Okay, with this we have completed the class. Okay. That